Acid-base equilibrium. Factors that affect acid strength and the stability of the conjugate base. In this tutorial, we will be going over factors that affect acid strength, the stability of the conjugate base X-1, and an overview of oxyacids. Factors that affect acid strength. The polarity of the HX bond, where X represents an anion. Molecular acids must contain a polar bond. Bonds between hydrogen and carbon atoms are not significantly polar. Thus, hydrocarbons generally do not possess polar bonds and are considered to be nonpolar molecules. Let's look at an example of propane. In this example, the bond between the carbon and the hydrogen is a nonpolar covalent bond. They have similar electronegativity values, as carbon is 2.6 and hydrogen is 2.2. Another location of a nonpolar covalent bond is between two carbon atoms within the molecule. Factors that affect acid strength. The strength of the bond. Strong bonds ionize less easily than weaker bonds. We need to consider the location of valence electrons in the electron configuration and the shielding effect by core electrons. Larger radii contribute to greater nuclear shielding by the core electrons and easier ionization of the hydrogen ion. The stronger the bond between the hydrogen and the remainder of the acid molecule, the weaker the acid. The higher the polarity of the bond, in other words, the more likely the molecule will ionize and release the hydrogen ion, the stronger the acid. Acid strength example, HF versus HCl. Let's consider the acid, hydrofluoric acid, with this structural diagram. HF contains a stronger, more stable bond than the bond in HCl. 2 core electrons in the first shell and 7 valence electrons in the second shell results in minimal nuclear shielding and a shorter bond length. The fluoride ion is less stable than the chloride ion due to the small size of the ion. Now let's consider hydrochloric acid, HCl. HCl contains a weaker or less stable bond than the bond in HF. A total of 10 electrons in the first and second shells compose the core electrons. 7 valence electrons in the third shell results in greater nuclear shielding and a longer bond length. The chloride ion is more stable than the fluoride ion due to the larger size of the ion. An ion that is the conjugate base of a weak acid is a weak base and is unstable. An ion that is the conjugate base of a strong acid is pH neutral. In other words, forms solutions that are neither acidic nor basic and is stable. So a strong acid like HI will have a negligible base of I-1, where I-1 is a stable ion. A weak acid like acetic acid has a conjugate base of a weak base, and that weak base of this acetate ion is unstable. Let's look at this in more detail. In this first reaction, we have HCl reacting with water to form hydronium ions and chloride ions. HCl is a strong acid that completely ionizes in water to produce hydronium ions and chloride ions. In this next reaction, we're looking at the chloride ions reacting with water, and we notice that there's no change in pH. The chloride ion has a relatively low affinity for hydrogen ions, so it does not ionize the water and has no impact on pH. The chloride ion is the conjugate base of a strong acid and is stable. Let's now look at the reaction of HF reacting with water to form hydronium ions and the fluoride ion. HF only partially ionizes in water and exists mostly in the molecular form. Hydrofluoric acid as a weak acid is more stable as a molecule. Reactants are favored in this chemical equilibrium equation. If we look at our next reaction, fluoride ions react with water to produce hydroxide ions and hydrofluoric acid. The F-1 ion readily accepts hydrogen ions from water. The fluoride ion is the conjugate base of a weak acid and is less stable than a molecule of hydrofluoric acid. Products are favored in this chemical equilibrium equation. Oxyacids. Acids that contain one or more OH bonds, where the OH bonds and possibly additional oxygen atoms are bound to a central nonmetal atom. In oxyacids, the central atom is a nonmetal and does not easily give up the hydrogen ions from the OH bond. The substance will become more acidic as the electronegativity of the nonmetal increases. 2 rules. Rule number 1. For oxyacids that have the same number of OH groups and the same number of oxygen atoms, acid strength increases with the increasing electronegativity of the central nonmetal atom. So we have HClO, HBrO, and HIO with their associated structural formulas. For HClO, the Ka is 3.0 times 10 to the negative 8, where the electronegativity of chlorine is 3.2. We compare that to HBrO, which has a Ka of 2.5 times 10 to the negative 9, where bromine has an electronegativity of 3. So HBrO is less acidic than HClO. HIO has a Ka of 2.3 times 10 to the negative 11, and the I has an electronegativity value of 2.7. Out of the 3 acids here, HIO is the weakest acid when we examine the Ka value. You should be able to predict this trend without the electronegativity values based upon the periodic trend of electronegativity decreasing down a group. Rule number 2. For oxyacids that have the same central nonmetal atom, acid strength increases as the number of oxygen atoms attached to the central nonmetal atom increases. Increasing the number of oxygen atoms on the central nonmetal atom does a number of things. First, it's going to increase the oxidation number of the central atom. Next, it's going to pull the electron density away from the OH bond towards the more electronegative central nonmetal atom. This increases the polarity of the molecule, which favors the loss of the hydrogen ion. It will also increase the stability of the conjugate base. So here we have 4 acids: HClO4, HClO3, HClO2, and HCl, all that differ by 1 oxygen. HClO4 and HClO3 are considered strong acids, so they do not have Ka values. We notice that the Ka value gets smaller as the number of oxygens decreases. We can also look at the oxidation number on the chlorine as we go from a strong acid to our weakest acid. So if we assign oxidation numbers, hydrogen has a charge of +1, oxygen is -2, +1 times 1 gives us 1, -2 times 4 gives us -8. So the oxidation number on this chlorine has to be +7, as we see down here. For our next one, hydrogen is +1, oxygen is -2. We multiply those by our subscripts, so we'll have +1 and -6. So our oxidation number for chlorine in this acid is +5, as we see here. For our next one, HClO2, hydrogen is +1, oxygen is -2. We multiply those by the subscripted numbers, so +1, -4, chlorine is going to be +3. And finally, H is +1, O is -2. We multiply them by the subscripted numbers in the formula, so +1, -2. Our oxidation number on the chlorine has to be +1. So we can see a decrease in the oxidation numbers on the central atom as the acid becomes weaker. The labile hydrogen has a lower ability to deprotonate when there are less oxygen atoms bound to the central atom. So remember that labile hydrogen is the hydrogen here, 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 and here. So what did you learn? We talked about factors that affect acid strength, the stability of the conjugate base X-1, and an overview of oxyacids. Need more help? Feel free to contact me. Have a great day.